Okay, we have another question here. It says a particle is raised from rest at a point A, 1 meter from a second point O. The particle accelerates towards O and moves with a simple harmonic motion of time period 12 seconds, and O is the center of acceleration. In simple terms, they are giving us the equilibrium position. Find how far the particle is 1 second after the release. So start by putting a simple sketch for what we have there. Okay, so this one I'm going to be with. So in my solution, I have, this is my L. This is where the particle is going. So this is my point O. So this is my point O. They're telling me if this is A, they're telling me that it's 1 meter from a second point O. So from here up to here we have 1 meter from O. That's it. Now, if we are to summarize the question, they're telling us that time period. So they are giving us period as 12 seconds. Okay, what else are they giving us? So they are giving that find. So in part A, they want us to find how far the particle is. So they want us to get x after 1 second when t is 1. Now, of course, you know that the equation I'm going to use is x equaling 2 r cos omega t. So that calls for the meters that we need our omega here. We need the amplitude, but the amplitude is not there. I think you can see from here up here is always our amplitude. So our amplitude is 1 meter. All we need is this. So how do we add that? We know that always our period is given by 2 pi over omega. So this one is 12 equaling to 2 pi over omega. When I cross 1 pi, you see that I'm going to have my omega as pi over 6 rad per second. If I have this, now I can every calculate here. Remember, I want this distance. After 1 second, so that's all I want. So here my x is going to be, amplitude is 1, then cos of this one, you see that is pi over 6, then times my t after 1 second. So that my x is going to be cos of pi over 6. But know that this is 6 divided by pi, that's going to be pi divided by 6, that's the third. And cos of 30, know that all is going to be root 3 over 2 meters. So that's how this particle is after 1 second. But when you are pressing your calculator, this should be in radians, as simple as that. Then part B, they want us to get how many seconds after this is the particle at the midpoint of OA. So my part B, now here again, get it a bit careful. So this is my ideal A. So this is my O. O. So it does that from here up to here we have 1 meter. Up to here. So midpoint is going to be, of course, the midpoint where we have 0.5 meters here, then 0.5 meters there. So the one at the time we are going to use to cover this one, T1, to cover that. So that's what they want us to get this time. T, let me call it T1. From here, when we are midway for the first time, so if it's seriously from here, this is where it's the distance. To come here for the first time, this is the distance we've covered. We need time. So using our equation, so our x equaling, so Roman numeral 1. Our x is equaling 2r cos omega t. Of course, no, we are this equation from the start. We are using them. So we need time. So we have the distance from here to here. It's going to be 0.5 equaling 2. Now our amplitude, of course, now the amplitude we've covered. Of course, for it is going to remain 1. The amplitude, this formula works for the amplitude from here up to here. So that our amplitude is 1. Then cos our omega is pi over 6, then times t1. It's the time I'm looking for. So this side I'm going to be with the x, which is 0.5. So I have 0.5 equaling cos of now pi over 6 t1. So when I get the inverse here, I have pi over 6 t1 equaling to cos inverse of 0.5. Your calculators should be in radians when you are pressing this. So my t1 is going to be 6 cos inverse of 0.5 all over pi. And you can able see cos inverse, that's going to give a cos inverse of 30. I think that is going to give us 60. I mean cos inverse of 0.5 is 60. 60 in radians is pi over 3. The 3 cancels and the pi cancels, which is going to give us 2 seconds. So it means from here up to here, the particle is going to use 2 seconds. Then remember 2, the second time. So for the second time, now it means it's going to come, it covers this, then it comes back here. This is the point, the midpoint of OA. So it means that we are going to reuse the time we have from here up to here. But because we have this time already, what we are going to, let us just say, let us get the time for the whole journey from here to here up to here. That's a complete cycle, and that is always a period. So and then we subtract off the time we need from here up to here. We shall be getting the time, we shall use from here, then up to here, as simple as that. So that's a simple explanation. So my time there, so my time is going to be t minus t1. I'll get the period. Remember the period will come from here, coming back and then here. But if I have this time I used for this, that means that to come back, I'm going to get the time for the wall. Then I subtract of this, I'll be getting the time for the from here up to here. So that's the idea. Okay, so our period, they gave us our period as what? Our period was 2 seconds, then minus our T1, which is 2. And so the time here is 10 seconds with ease. You see? They are very easy things. So that's how you handle that. We are going to see more examples. I wish you well. You see, simple harmonic motions, they are things very easy and direct. But here, don't forget that the calculator should be in radians. Let me even put that in brackets so that you can get it properly. Calculator in radians. Simple, and that's it. So, that's all we had. I wish you well.